So let me try to finish up the stream algorithms and then get as far as I can on page rank, and we will finish that. We'll finish page rank probably tomorrow. I think I can get through everything I planned because my last 2 lectures are kind of short. Anyway, okay, we talked about counting distinct elements. There's a generalization using something like the Flageolet-Martin technique, but it's a little bit different. And it's worth seeing. So the setting again is we have a stream. There are n different possible values of that that can appear in that stream, and now I want to let m sub I be the number of times the ith value occurs, and then I'll define the kth moment to be the sum of the kth powers of the counts, the mi's, summed over all I. So let's look at the 0th moment. Well, mi to the 0th power is just 1, so I'm counting 1 for every different element that actually appears at least once in the stream. So that's count distinct, and that's what so we already know how to do 0th moments. Well, first moments is just summing the counts of the number of elements. It's the sum of mi's over all I. Well, that's the number of occurrences of elements in the stream, or just the length of the stream. So that's a really easy case, right? I just count the number of elements. Each time I see a new element, I add 1, and that's all I need to get the first moment. Now, second moment's a little trickier. It's called the surprise number, and it's a measure of whether I have an even or uneven distribution of elements that actually appear. So, to give you an example, suppose the stream length is 100, and I tell you that 11 different values have appeared. Now, what do you expect the distribution of those elements to be? Well, the most unsurprising case would be when they all sort of appear the same number of times, or as close as you could get. So since there are 11 values, what would happen is 1 would appear 10 times, and the other 10 would appear 9 times. Now, if you sum the square, the second moment is the surprise number, so you sum the squares of those numbers, you get 100 squared plus 10 times 9 squared, that's 910. And that's the smallest possible surprise number in this situation. What would be really surprising, though, is if one of the elements appeared 90 times and everything else appeared once. So then you'd have 90 squared, that's 8100, and then 10 1 squareds, which would be another 10. So 8110, that would be the maximum possible surprise number. So, if I tell you the surprise number is 3000 or something like that, you say, well, that's kind of uneven, but not the worst possible, not as uneven as it could be, nor is it as even as possible. So that's all the motivation I can give you for this. So let's see, how could we estimate the surprise number? Again, you could count, if you wanted to, if you had the room to, you could just count the number of occurrences of each of the elements, sum their squares. But there's an interesting method. It's due to Alain Matthias and Szegedy, known as the AMS method. It works for any power, any moment, 2 or higher. I'm just going to do it for second moments. And like the Flageolet-Martin, gives you, you're going to run a number of different experiments. Just like in Flageolet-Martin, you computed tail lengths for a number of hash functions. Here, we're going to do a different experiments, but we'll combine them in the same way. That is, take averages of small groups and then the median of the averages. Okay, now again, where Flageolet-Martin used the tail of a hash function as its random variables, we're going to calculate random variables, which I'll call x a typical random variable. And again, we're going to compute, let's say, 100 different random variables and combine the values that we get for those random variables to estimate the surprise number. Each variable requires that I count something in main memory. And also, by the way, record. It's also going to be associated with a stream element. So x is really a stream element and an integer, which is the count of the number of times that integer has occurred under certain circumstances, which I'll describe. So again, let's start off assuming the stream has length n. Now, by the way, remember, streams don't have a length. Okay, but let's suppose that n elements have come in so far. Now I want to pick a random time to start my counting, that's the count that's associated with a random variable. And I want to pick the start time uniformly. So it's equal, it's going to, with probability 1 over n, it'll be the first stream element, with probability 1 over n, the second stream element, and so on. Okay, now, again, associated with that random variable will be the stream element that appeared at the random time that I chose. And I'm going to always call that green A. And then the value associated with this random variable will be n, the stream length, times the quantity, twice the number of that element, A, that has appeared in the stream starting at the chosen time. So it always appears at least once. And then I subtract 1 from twice that count. Okay. And by the way, you're going to store n once. As the stream grows, n changes. So we'll just store it once, keep account of the total length of the stream, and then associated with each random variable will be the value of that green A and the count of the number of times I've seen that A since I started counting. Okay, so what's the expected value of x? Well, first of all, the second moment, remember, is the sum over all A's, of stream elements A, of the square of the number of times that A appears. Now, the expected value of x is 1 over n. That's because we're going to average over all possible starting times of, well, what it says here is, okay, so we're going to sum, okay, it's 1 over n. So it's 1 over n and the sum over all times t. So we're averaging over all times t. N times twice the number of times the stream element at time t appears from time t on, and then subtracting 1. Okay. Now, the interesting thing, this is a sum over times t, but I could just as well have summed over A, the element itself. Now, this 1 over n is this 1 over n. That n is just that. Now, for any given A, again, the sum, the n times, the n is taken care of. So I just need twice the number of times that this element has appeared, minus 1. Okay, now the 1 is, there will be some time which is the last time that this A appears. And for that one, I'll get twice 1, which that's the only number, that the 1 will be the number of times it appears from that time onward, because this is the last time. And then minus 1, so it's 2 times 1 minus 1 is 1. Oops, wait a minute. Okay, the 3 is the time, the next to last time that A has appeared, because then it will be 2 times 2 minus 1 is 3. Then the 5 will be for the third time that A has appeared. So the third's from last time that A has appeared, so it's 2 times 3 minus 1 is 5. And then so on. And then the 2MA minus 1 is for the time that is the first time A appears. Because then it will, from that time on, all M sub A occurrences will be at that time or later. So it's twice MA minus 1. Now, what's this sum? Well, it's MA squared. That is, this sum is MA squared. I'll let you figure that out. So what you have is sum over A of M sub A squared. And that's exactly what the second moment is. Okay. Now, there are a couple of little fix-ups I want to do. First of all, the easy thing is, again, this is all based on there being a particular value of n. Okay, but in fact, n is changing. Every time a new stream element comes in, n grows by 1. Okay, so the value of x depends upon n, but it depends on it in a simple way. So you just keep n off to the side, and when you need to compute the value of x, you use the current value of n. So all you need really is the chosen element, green A, and the number of times that A has appeared since the randomly chosen time when things start. Now, the bigger problem is, suppose that we're going to store k different random variables, k counts. If you can store as many random variables as there are as the length of the stream, that is, if k is n, then you can just have one random variable for each position, but you can't. Eventually n grows too big. You have to have a fixed number of counts. So what that means is, as time goes on, sometimes you're going to have to throw away a random variable and start a new random variable at the current time. And what you need is what the objective that's outlined here. It says you want to know that the probability that any one of the n starting times is selected is the same, and in particular is k over n. And you want that to be true all the time as n grows. So, again, if I can afford to have k random variables, for the first k for the first k inputs, I'll just choose each of those times for one of the random variables. Now, suppose a new nth element arrives, and n is greater than k. So now I have to select which k of the n starting times will actually be the starting times belonging to my chosen variables. And again, each one has to have probability k over n. So when the nth element arrives, I know it has to be a starting time or a variable with probability k over n. So I flip an n-sided coin, and if it's with probability k over n, I choose the current element as the starting time for one of my random variables. And then if I don't choose the current element, then I leave all the random variables alone. If I choose it, I then have to pick one of the elements at the current random variables, I want to pick that with equal probability to throw out. Now, I'm not, here's the formula.
Why don't you just throw out the oldest one instead of...
Because then it wouldn't be random. Every starting time has to be equally likely to be chosen. Okay. Okay, so let's see. Well, first of all, with probability n minus k over n, I don't choose the current position. And then the probability of any one of the n minus 1 previous positions being chosen for a random variable is k over n minus 1. That's sort of inductive hypothesis. So that's one term in the probability for something being, for a particular position being chosen. And then there's probability k over n that the nth position is chosen. And now, in order for a previous position to survive, it first of all has to be previously chosen. So that occurs with probability k divided by n minus 1. And it's got to survive. Well, I'm going to throw out one of the k previously chosen positions, so it survives with probability k minus 1 over k. Now, I'm not going to do this, but if you simplify this, the sum of two terms, you actually get k over n. So that says that all the previous positions, as well as the new position, are chosen now with probability k over n. Okay, and that's, well, okay, I didn't say it, but you have these k samples. Each one gives you an estimate of the expected value of the second moment. Again, you do what you did in Flageolet-Martin. Take about log n of them in a group, take the average of a group, and then take the median of the average. Okay. So with that, I want to move, oh boy, time is wasting. I want to talk about PageRank. Okay. And this is a bit of a story. And I'm going to divide the story into the four parts. One is sort of the original PageRank idea. And then I want to talk about topic-specific PageRank, which is a newer idea that it turns out to be very useful. I want to mention the hubs and authorities algorithm, which is a related idea that has some well, it's got its own uses. And then I want to talk about what's called link spam. Does anybody know what did PageRank actually do for us? Okay. That is, why was Google a successful search engine? Look, before Google came along, I remember we discovered Alta Vista. Right? Alta Vista was one of the early search engines. And for a while, we were actually able to find stuff on the web using Alta Vista. And it was really good. Okay. And then there came a time when it would only give you crap. And, meaningless, you'd enter a search query, more or less like you do to Google or Bing now, but you'd get sort of random pages. I mean, what had happened? People who are trying to sell things on the web learned that they could fool Alta Vista. It's what's called term spam. Okay, and the idea was they could put words on their pages that you couldn't even see because they were in the same color as the background color, or use any of a number of other tricks, and make Alta Vista think that their page was about anything else, about anything that they wanted to, probably porn. And so we just weren't able to find real porn pages anymore. And then Google came along, and what PageRank does is it's a good measure of how how important the page is. Okay, so, if you're trying to see, if you're some little shoe store or something like that, you can put up a page on the web, but you can't ever be an important page. Okay, so Google would not give you that page. And all of a sudden, the world opened up to us again. Okay, well, unfortunately, spammers aren't stupid. And they have found ways to combat the effect of PageRank and make pages look important instead of just, they can no longer just fake what a page is about, but they can now try to pretend to make their page look more important than it really is. And that's the subject of link spam, which I'm going to talk about. Probably won't get to it today, but I'll get to it tomorrow, certainly. And it's a war. Okay, spammers try to disguise what they're doing so that Google will pick up their page and show it, and Google tries to figure out who's faking things and stopping them from doing exactly that. Anyway, so again, so this motivates the idea that importance was, solved a problem. It's not the last problem that needed to be solved, but it was something. It's something you need to know about if you're going to do if you're going to do search and protect against spammers. The notion of importance is a recursive notion. Okay, that is, what you want to say is that a page is important if important pages link to it. Okay, and roughly the notion of importance is the principal eigenvector of the transition matrix of the web, and I'll describe what that is. Another way to look at it, which we'll talk about, is with the notion of a random surfer. You land in a random page on the web, you follow a link out of it at random, where do you wind up? Well, you tend to wind up at pages like www.yahoo.com or www.amazon.com because the links tend to get you there. And that's the probability that you wind up at a page is, in some sense, it's important. The importance. This works well enough to combat combat term spam effectively. Okay, so first of all, what's the transition matrix of the web? Okay, I'm going to assume that the pages are indexed, the numbered 1, 2, 3, and so on, and the ith page will be represented by both row and column I in the matrix, and the element m of ij, that is the element in row I and column j, will be 1 over n if page j links to n pages, including page I. Okay, so again, if j doesn't link to I, then mij is 0. If j does link to I, then the value is a fraction. It's 1 over the total number of pages that j links to. So you can think of it again in terms of the random surfer. If they're at page j, then the probability is 1 over n that they will be at any of the pages that page j links to, and it's 0 for the other pages. So, for example, if j links to 3 different pages, I is one of them, then you get 1/3 in row I and column j. If x is not one of the pages that j links to, then there'll be a 0 in the row for x and the column for j. Okay, so again, the web, of course, is just way too big for me to give you to show it to you, except it's been growing sort of exponentially since it was invented. And so if you go back in time, eventually you'll come to a web that's small enough that I can give you an example. But anyway, this is sort of what I've been saying all along, is that you can think of a surfer walking on the web if V is the current distribution of the probability that the walker is at a certain page, then M, the matrix M multiplying V, the vector V, the multiplication on the left, will be the distribution of the walker or walkers at the next time step. Okay. Okay, so, okay, now I don't know, if you're familiar with Markov processes and so on, there are always these little glitches which we'll try to fix up. But basically, if you take any distribution of the walkers are distributed among all the pages of the web in according to some vector V, and you keep multiplying that vector by M over and over again, eventually you get the limiting distribution of the walkers. Okay, and by the way, that is the principal eigenvector of this matrix. Okay, now that's okay. Now this is the lead up that I was trying to give you, but I did it too early. Okay, so but you go back to 1839, and it turns out there are only 3 pages on the web. Okay, and these are the arrows of the links. So just let's see, to give you an example, the Yahoo links to Amazon and to itself. So if we look at the column for Yahoo, it's got 2 links out, so the non-zero entries will be a half. And in the row for Yahoo, there's a half because Yahoo links to itself. And there's also a half in the row for Amazon because Yahoo links to Amazon. It doesn't link to Microsoft, so there's a 0 here. Okay, so this web graph is represented by that matrix. Okay, again, Amazon splits between Yahoo and Microsoft. Microsoft points only to Amazon, so you get a 1 in the column for Microsoft and the row for Amazon. Okay, so that's the web we're going to use as our example. Okay, now again, the limiting value of V will be that value, the vector V that satisfies the equation up there that says V equals MV. Well, the trouble is there are no constants here in this equation, and therefore there isn't a unique solution. If V is a solution, then 10 times V will also be a solution. Okay, so you can't just solve this by Gaussian elimination, but you don't want to anyway, because again, if the number of rows is not 3 but 1 billion or 1 trillion, you're not going to solve this by Gaussian elimination. Anyway, there's another method which tends to work pretty well in these situations. It's technically called relaxation. What it really means is you start with any old value of V, and you multiply it by M, and then you multiply that by M, and then you multiply that by M, and so on. And after about 50 iterations, you get close enough to a vector that satisfies this equation. Okay, so I'm going to start with the vector of all ones. Now, in practice, they usually start not with ones as the initial component, but 1 over n, where n is the number of pages, so that the sum of the elements is 1. And then you can sort of think of it as a probability that the walker is at a given place. But I'm going to start with all ones that eliminates some of the fractions and I think makes it a little bit easier to follow the arithmetic. Okay, so we're just going to apply m to v over and over again until we get a limit. So if you remember, these were the equations. That is, the probability of being at Yahoo at a given step is a half the probability of being at Yahoo at the previous step, plus a half the probability of being at Amazon at the previous step, because both Yahoo and Amazon link to Yahoo along with one other page. Okay. And the probability of being at Amazon is half the probability of being at Yahoo plus the entire probability of being at M, because Microsoft links only to Amazon. So you can think of while these are you'd like these to be equations, and ultimately you want to find values of y, a, and m that satisfy these equations. Think of the equals as an assignment statement. Okay, so we're going to start off with all ones for both y, a, and m. Now, the next iteration, well, I'll just do a quick example. The new value of a is y over 2. Well, y is 1, so half that is a half, plus m. M is also 1, so it's a half plus 1, and so a is 3 halves. Now, I apply the same equations to these values for y, a, and m, and I get these values. And then when I apply the equations to these, I get these, and so on. Well, where is it headed? Turns out that in the limit, you get y and a are both 6/5 and m is 3/5. And if you just check it, you can see that these values actually do satisfy these equations. Okay. Now, I want to show it to you again very quickly as walkers. Oops. Okay. Here I'm showing you, let's say, 10 walkers starting out at each of the nodes, and I've colored them differently. I'll preserve the colors so we can see where things go. So in one step, for example, all the blue Microsoft guys are now at Amazon. Half the green Yahoo guys, half are still at Yahoo, half are at Amazon, and so on. The red Amazon guys, half are at Yahoo, half are at Microsoft. One more step, there's a little more mixing. Another step, still more mixing. And in the limit, of course, there will be 12, 12, and 6, again, which is the ratio. It's 1 to 1 to a half. And as I've shown here, there will be, where you started from doesn't matter. You're equally in the limit, you're equally likely to have come from any place. So the 12 guys at Yahoo, 4 of them will have come from each of the 3 places. Now, I wish the world were that simple, but in fact, the matrix of the web isn't really a simple stochastic matrix like that. First of all, there are pages that have dead ends that just don't have any links. Now, if I imagine the walker, if a walker gets to a dead end page, where do they go next? They don't, they disappear. What happens then with a dead end eventually causes all the importance or all the walkers or however you want to think of it to leak out of the system, and then eventually everything goes to 0. And then you can have a group of 1 or more pages that are what are called spider traps, and they were again put there intentionally so that the crawlers on the web, spiders, if you will, once they got into one of these pages, they could never get out. Well, see, you can do that. You can always create a page that links only to itself, or you can create 10 pages that link among those 10 pages, as long as they don't link anywhere else. So you're going to have spider traps all over the place. So I just want to show you what happens. In this case, Microsoft has become a dead end. Remember, Microsoft used to have an arc to Amazon. Now I've just removed it. So when you get to Microsoft, you don't go anywhere. So this corresponds to the column for Microsoft now. Instead of having a 1 here, it's all zeros. And well, here are the equations, and I'll just show you how things go. But the sum is going towards the values get smaller and smaller, and eventually, if you let it go long enough, they become 0. Or another way to look at it is, in terms of the walkers, here are our initial walkers. Remember, the blue walkers aren't going to go anywhere. So the next step, they're gone. And now, at the step after that, half the Amazon guys will disappear because they've got nowhere to go. And then these 3 guys, which happen all to come from Yahoo, they will go, and again, eventually, they're all gone. They've eventually found their way to Microsoft, and then they're out. So that's no good. Okay. Another situation of spider trap. Again, this is the simplest form of spider trap. Microsoft links to itself, but nowhere else. So now, in terms of the matrix, it corresponds to, well, it's still a stochastic matrix, but again, there's the one in the column for Microsoft happens to also be in the row for Microsoft. So again, here are the equations. I can show you if you apply them, the numbers. Again, Yahoo, the Y and A gets smaller and smaller, and the M gets bigger and bigger, and eventually becomes 3. And so everybody has wound up at Microsoft. In terms of the walkers, you can see what happens after 1 step, after 2 steps, and then in the limit, everybody's at Microsoft. Okay, so when Brin and Page first implemented PageRank, they were aware of these problems, so they didn't exactly compute, do what I suggested, start with a vector v and then keep multiplying by m times m times m times m. The way to think of it is that they taxed, they taxed each page, so that if you had at one round a page rank of 10, let's say, maybe there'd be a 20% tax. So they'd take 2 away from you. And as taxes are supposed to do, they're distributed evenly among everybody. Okay, that's how taxes work, right? Well, at any rate, they would give everybody an equal payment. They're going to certainly take the tax, distribute it evenly, but they also, at the same time, they might as well take what's going to fall out in the dead ends and distribute that evenly as well. It doesn't matter, you could do that or not, but the point is that you're going to add a constant to every page. Every page gets the same amount, again, which might be based on the tax, might not. At any rate, what this is going to do is it's going to model a process in which you're randomly walking on the web, but you have a fixed probability of just deciding to leave the system and go away. And in addition, we're going to introduce some fixed number of walkers at each page at each step. And then we'll just see how the walkers distribute. So here's the equation where, again, Microsoft is a spider trap, but we're going to tax everybody 20%, and we will put 0.2 into each of the 3 pages as well. So the equations now, remember, Yahoo used to be a half of its old value and a half of Amazon's value. Now it's those 2 values summed, but then multiplied by 4/5, because that's the part that isn't taxed away. And then we'll give Yahoo its share of the total tax, which would be 2/10. And so these are the equations, and I can show you what happens. Well, for example, Amazon is y, at the second round, y over 2, y is 1, so this y over 2 is a half, and then 4/5 of that is 4/10, and then plus 2/10, that gives you 6/10 as a value. And Microsoft, which of course is still accumulating its own value except for what gets taxed away, is still growing, and it grows even more at the next round and more at the next round. But in the limit, it turns out that things distribute this way. So Microsoft still gets the biggest share, but it doesn't get everything. Okay, and it suggests that Yahoo is more important than Amazon. Not a surprise, because if you look at the formulas for Yahoo and Amazon, they both have a link from Yahoo, but Yahoo also has a link from Amazon. So you kind of expect that a walker should be more likely to wind up at Yahoo. Okay, now the next improvement in this idea was what's called topic-specific PageRank. In other words, PageRank works on the assumption that any page is in principle equally likely to be of interest to you. But suppose you know I'm the kind of person who's really only interested in sports. So if I issue a query like Jaguar, I'm probably interested in some team named the Jaguars. There is one. Okay. If I'm interested in automobiles, I'm interested in the Jaguar car. That's, and so if you know what topics I'm interested in, you can bias the PageRank in such a way that I will more likely to see pages that are in the topic that I'm interested in. Now it's a little bit tricky to do that. But it can be done, and it has been done. And the idea is, it's sort of a generalization of the taxation method. That is, we're going to assume that you have that the way walkers walk the web is not they have a fixed chance of giving up. That's what the tax was. But they have a fixed probability of teleporting. Okay. Now, if you can teleport to any page with equal probability, then that corresponds to the taxation scheme. Okay. But if, for example, I want a PageRank that is specific to sports, I'm going to identify certain pages that are known to be pages about sports, and I will teleport only to those pages. So this is going to force the walkers to be near, to land frequently on a page that is a sports page. And the assumption is that the sports pages are going to tend to link to other sports pages. So as they follow these links, they will, the longer they walk, the less likely it is that they're at a sports page, but then they have some reasonable chance of teleporting again, and when they teleport, they always teleport back to a sports page. So let's see how this works. Now I'm going to go back to the original web where Microsoft points to Amazon, not to itself. I'll assume there's a 20% tax, and the topic is software, so only Microsoft is in the teleport set. And this is my attempt to draw Doctor Who's phone booth, which I've since learned is called a TARDIS. Yeah. But, okay, so the first thing that's going to happen is, well, think of it as tax. 1 out of 5 of the walkers at each of the pages go into the phone booth. And now the remaining ones do their dance. They pick a random out link and go there, and that's what happens. And then all the guys in the phone book go to the teleport set, which is in this case just Microsoft. And then same thing happens, tax to the telephone booth, shuffle around, and then everybody goes to the to Microsoft. Everybody in the phone booth goes to Microsoft. Well, in this particular case, it keeps the page rank of Microsoft artificially high. You can sort of, so this is actually pretty much the limit of what happens. Now you have to, okay, now how do I pick, let's say I'm interested in sports. How am I going to pick pages that are sports pages? Well, one way you can do this is you use something like Open Directory, which is a small directory of pages that have been hand classified. And you say, if it's been classified as sports, then it really is a sports page. But of course, there are lots of other sports pages. But you can use those pages to see what words are mentioned. So you're going to get the sports pages are going to use certain words like kick or what that appear much more frequently in those pages than average. Than a random page. And so then you sort of learn the words that the topic is about. And now you can look at any page on the web and decide whether it's a sports page by how frequently the sports words appear on it. Okay, so doing that you can get a reasonable teleport set. Okay, now again I'm going to come back to this again, not today, but tomorrow. Another application of the topic-specific page rank is trying to avoid these what are called spam farms. The idea is now I'm not really interested in a topic, but I'd like to know that when my walkers teleport, they teleport to a trusted page, so they tend to stay out of the pages that are actually what are called spam farms, things that are on the web for the sole purpose of fooling Google and giving undeserving pages a higher page rank than they deserve. Now, in this case, what you do is you need to find a set of trusted pages, and we'll talk about that again. But a simple case is if you're in the .edu domain, or one of the subdomains, I guess like ac.se or something that you can only get into if you're a real university or educational institution of some sort. There you're going to be you're not a spam farmer. You're a real you're a trusted organization. So you use the teleport set becomes the set of trusted pages. Now, with that, let me talk about something else. This is an idea called HITs, or Hubs and Authorities. There's an interesting story behind this. John Kleinberg was a postdoc at IBM at the time that Brin and Page were developing Google and PageRank. And a couple of months after they came up with the PageRank idea, Kleinberg invented something which he called the Hubs and Authorities. And it's in some sense, he didn't know about PageRank at the time, but it's sort of it's a similar idea, in some sense more complex and more powerful, but in fact not something that turns out to be all that useful when you're starting a company. And so Kleinberg did not become rich, and Brin and Page really did. Kleinberg, by the way, though, did win a MacArthur Fellowship. He's a really bright guy, a good guy. Now teaches at Cornell. Anyway, I thought, let's see, I have about 10 minutes left, and that's probably what I need to just explain how the hubs and authorities idea works. Okay, so remember, PageRank is a simple recursion. It says a page is important if important pages link to it. Okay, so hubs and authorities starts out with two mutually recursive two mutually recursive concepts. One is a hub. A hub links to many authorities, and an authority is linked to by many hubs. Okay. Now, what it amounts when you solve for the degree of authority or the degree of hubbiness that a page has, what it amounts to is authorities turn out to be the places where you can find information at that page. So, for example, each course at a university will have its own homepage. And that's where you go if you want to find information about that course. A hub generally doesn't provide information itself, but it will tell you where to go to find the information. So, for example, there will be, each department will have a page, lists all its courses. You don't learn anything from that, but you do find out from the hub where you can go to learn things. Okay. Okay, so that's the distinction between hubs and authorities. Okay, so to formalize it, we're going to talk about a matrix A of ij. I is the row, j is the column. And I'm just going to put a 1 if page I links to page j, and 0 if not. Now notice, when I defined PageRank, first of all, the links were going the other way. Here the links go from row to column. In PageRank, it was defined so that the links go from column to row. So as a result, the transpose of the A matrix looks like the PageRank matrix that I called M. However, it's still not the same because the matrix M had fractions, 1 over n if a page linked to n pages. Here, in the A matrix, you just put a 1 means a link, doesn't matter how many other links there are coming out of the page. Okay, so here's our old web, and here's the matrix. I'm sorry, it's not the, well, I changed it a little bit. I added an arc from Yahoo to Microsoft. So now Yahoo links actually to itself, to Amazon and Microsoft, so it has 1, 1, 1 in its row. Amazon links to Yahoo and Microsoft, but not to itself, so it gets 1, 0, 1. And Microsoft, again, links only to Amazon, so it gets 0, 1, 0. Okay, so that's the matrix A. The matrix, the transpose is what you think it is. Now, we can take A, multiply it by itself, take powers. Same with A transpose. The trouble is, since since you tend to have a lot of 1s in any row or column, the powers of A or A transpose are going to grow. And they'll grow exponentially. They'll roughly multiply, since the average page has about 15 outlinks, the numbers will be 15 times larger each time you multiply by A again, or A transpose. So you need scale factors. What scale factors you use are not important because you really only care about the relative hubbiness or relative relative authority of pages, and you only need a scale factor so that the numbers just don't grow bigger than you can conveniently store in a 32-bit or 64-bit number. Okay, so again, we're going to let H and A be the vectors. These correspond, they're like the PageRank vectors, but the components for H, the ith component of H, is the hubbiness of the ith page, and the ith component of A is the authority of the ith page. And if you remember, the hubbiness of a page is the sum of the authorities of the pages it links to. But then I have to add the scale factor lambda. I don't know what it is, but it'll be some small fraction, like a 15th. And similarly, the authority of a page will be some scale factor mu times the transpose of the matrix A multiplying the hubbiness vector. Okay, so these are your equations. And you got to solve for H and A. Well, it turns out in principle, you can substitute for A here, this thing, and that gives you that the hubbiness is lambda times mu times A transpose H. And you can get a similar equation for the authority. It's, again, this constant lambda mu. We don't know what it is, but it's just some scale factor there to keep the numbers within bounds. And now it's A transpose A times the authority. So, for example, I could compute H by iteration, start again with some random, any vector I liked for H. I could just multiply that by A transpose. And then I could pick a suitable value of lambda mu. Doesn't even matter. It doesn't even have to be the same at each iteration, just as long as I keep the numbers from growing too large. Okay, so here's an example. Okay, what I have here, I started with the matrix A transpose, obviously is that transposed. I multiply A times A transpose, I get that, I get A transpose A, and I get the fourth of the matrices there. And now, if I'm computing authority, then I'm going to start with, let's say, a vector of all ones, and I'm going to multiply by this matrix. So 2, 1, 2 dot producted with 1, 1, 1, that's 5. 1, 2, 1 dot producted with 1, 1, 1 is 4, and so on. So I'll get the next round, I'll get 5, 4, 5. If I multiply by this matrix again, I'll get this, 24, 8, and that. And I better, at some point, I'd better start scaling these things down. But again, it's just the ratio. It's the fact that here it's 114 to 84 to 114. The fact that the authority of Yahoo and Microsoft seem always to be the same, that's what's important. And they're bigger than the authority of Amazon. Well, it turns out these are the limiting values. I could also do hubbiness, start with 1, 1, 1, and now multiply by this matrix. And I do that, I get these numbers. And, well, again, to some scale, I'll get these. It says that the hubbiness of Yahoo is higher than that of Amazon, which is higher than that of Microsoft. Okay. Well, one other thing you have to be a little careful of. What I did was I just computed the matrix A transpose and A transpose A. You don't really want to do that because they're not as dense as A and A transpose. Again, if you think of each matrix has 15 ones in each row and column on average. You multiply A by A transpose, you're going to get 225 ones in each row and column. So it's, you don't want to actually do that. But so I'm going to, let's say if I want to compute the hubbiness, by the way, first, if I compute the hubbiness, then it's very easy to compute the authority by one more multiplication of a matrix, because again, the H and A are related by multiplication of either A or A transpose. So if let's say if I want to compute the converge to the hubbiness, let's say I start with hubbiness 1. I multiply by A transpose, which, by the way, gets me the first estimate of authority. Then I can multiply by A to get the next value of H. And here I'm only multiplying by these very sparse matrices, which is more efficient than multiplying A and A transpose first and then doing one matrix vector multiplication. And then at some point, I have to keep scaling at some point. Okay, well, this is really just saying why you want to multiply by A transpose and then multiply by A rather than multiplying AA transpose once and multiplying by the product. Okay, well, I guess I'm sorry. I'm not. I think it's the time is actually is up. I'm going to stop here. But anyway, I think this gives you enough. If you ever wanted to do hubs and authorities, you know how to compute them as efficiently as you can. Okay, and tomorrow we'll take up link spam and everything else. Okay. Thank you.